Dear students, welcome and thank you for tuning in to this video with me, Dr. Loay Al-Zube. We are still talking about statics and dynamics. In this lecture, we are going to discuss friction. Many times when you're driving, you will hit the brakes and then the car will stop. How can we quantify the friction force that caused the car to stop? We are going to discuss the characteristics of friction. Also, we're going to learn how to draw a free body diagram that includes friction forces, and we're going to be trying to create the equations of equilibrium and involve in them friction. We have learned so far in statics and dynamics what are the external forces, what are our reactive forces. We talked about member forces over trusses, and we learned about also internal forces. Now we add friction forces, and after understanding friction, we should be good actually in analyzing any static system by constructing the equations of equilibrium and finding the unknowns of that particular system. We don't want to miss on this lecture because it's going to provide us with the big picture, the complete picture of static and analyzing forces in static equilibrium. If you are a bike rider, you know that designing bikes or cars or any vehicle, it is important to understand frictional forces. And any time you are going to be hitting the brakes, it's a good example and a good application of how friction forces act, and it's important for us to understand a couple of things about friction. So when you apply the forces on a bike tire brake pad, how can we find the magnitude and direction of a resulting friction force? So this is another reminder that friction is a force, and we need to identify magnitude and direction. It is similar to external forces or similar to reactive forces. How can we create a free body diagram that includes a friction force? And that is going to be the topic of our lecture. In general, friction is defined as a force of resistance, and it acts on body and it prevents slipping of a body relative to another body. So if you have a block that is placed on the ground and you want to see a friction is actually the force that prevents slipping or sliding of that block on the surface of the ground, which is the second body. There are a lot of concepts we need to understand. However, again, in general, experiments shows that frictional forces act tangent, parallel to the contacting surface, and in a direction opposing the relative motion of motion or the tendency for motion. So if you look at this structure here that we have, you can see that this is your block, and we are trying to pull the object in the positive x direction. So our friction force is going to be actually in the opposite direction here, right? Going to that direction. And the reason why we have this force is actually it's the summation of multiple smaller microscopic forces that is the result of the roughness of the surface between the block and let's say the ground where the block sits. So if you look into the microscopic view, you can see that you have a frictional force in that direction, and you have a normal force created because of the weight, the infinitesimal weight or the microscopic weight, and the summation of these two is actually a resultant force in that direction. However, we want to relate friction to normal force. That is actually the most important part of our analysis of friction. For a body shown in the figure, so let's say we're going back to our block. Again, we are studying statics, so equilibrium is very important for us. So in order to have such a block to be at equilibrium, account also in keeping in mind that we're going to account for friction, we have actually multiple conditions that needs to be true, and those conditions come from our previous analysis of equilibrium. The first one is summation of forces on the x-axis should equal to 0, summation of forces in the y-axis should equal to 0, and summation of moment around an arbitrary point should equal to 0. If we want to look at these three equations of equilibrium, you can see that F and P they're on the x-axis, right? So P is in the positive x-axis, and F is in the negative x-axis. In order to have equilibrium on the x-axis, which is the first equation, P should equal to F. That's the first condition. The second condition is also similar, but in the y direction. So the normal force should equal the weight of the object in the opposite direction. And that's my normal, and that's my weight, which is placed in the center of gravity. The third condition, which is related to the moment, is actually we have a couple moments. So if you look at the y-axis, you have your n, you have your w, and there is a distance of x. So they're equal in magnitude and opposite in direction, and there is a distance between them. So there is a tendency to rotate counterclockwise. So w multiplied by x is going to rotate counterclockwise. P and h is also two equal forces, opposite direction, there is a distance, so there is a tendency to rotate clockwise. So it's counterclockwise, W and N, and you have a clockwise on the P and H. And these are the conditions that need to be satisfied in order to have equilibrium when you are considering friction in a system. A quick now overview about again the characteristics of dry friction, and it's worth noting here when we say dry friction, it means that we are looking at two objects that they are sliding or there is slipping or sliding on a surface between them under the conditions that we do not have lubricants. And that is what we mean by dry friction. To study the characteristics of friction force, and that is actually the force that we would like to identify, we need to assume that tipping does not occur. We don't have tipping. And that in another way, that means that the distance between the friction force and the acting force, which is the external force, is small, as well as width to be large. And this is going to reduce the possibility of tipping. Let's say we are assuming that the object is sitting on the surface of the ground. In order to study friction and to quantify how the friction force will behave, we will start with 0p here. So if we are plotting p against friction, so that's p on the x-axis, and I'm plotting it against f on the y-axis, I will start with 0. So 0 force, pulling force. As we increase P, the friction force will increase. Please remember that as we move in this direction, as we increase the forces, the object is still on the ground. It's not moving. It's still static in its place. So as we increase the magnitude of P, F is going to follow that pattern, and experimental data shows that the friction force varies with P as shown in the figure. So as you increase P, the friction force will keep increasing until you reach a point here at the top, and that is what we call the static friction force. After this point, actually, and this force, the object will start moving. So from this point here to this point here, the object is not moving. Once it starts moving, the friction force will go down, and then it goes, a steady state value. And that's called the kinetic friction. And the maximum force reached actually before moving is called the static friction. It is very important to understand how is that figure relates to the behavior of friction force. So the maximum friction force, again, which is this force here, is attained just before the block begins to move. So before this point, the block is not moving, and after this point we have the movement, and this point is called actually impending motion. So at this point we have what we called impending motion. The value of the force is found to be using the friction, static friction equals mu s multiplied by n, where mu s is called the coefficient of static friction, and Fs is the static friction force, and N is the normal force, which can be calculated by looking into the weight. The value of mu s depends on the two materials in contact. And that's another coefficient value that it depends on the materials that the block and the surface are made of. But keep in mind that we start with zero force. The maximum friction force is actually before movement, and that is called impending motion. Once the block begins to move, the friction force typically drop, and that's what we see in the experimental data. So we were here, and then it dropped down because of the starting to move, and the friction typically drops, and it's given now with another formula, but it's similar in structure in its components. So we have kinetic friction force equals mu k multiplied by n. Mu k is the coefficient of kinetic friction. Remember, because we're moving now, it's called kinetic friction, and n is the normal, again, is measured by the weight of the block. So before movement, we're going to, if you have a system and we need to analyze it, you might be given mu s as well as mu k. If the question is telling us that we are impending motion and it's before it starts to move, we can use the mu s formula. If the question is telling us that the object is in motion, then we will use the mu k, which is the coefficient of kinetic friction. So this is important. So in our analysis for equilibrium, we will add another equation if we are considering friction. So we will start with the summation of forces on the x-axis equal to 0, summation of forces on the y-axis equal to 0, summation of moment around the point equal to 0, and we will add a fourth equation, which is F equals mu n. And depending on the question that we are given, the force is either static frictional force, or it's a kinetic friction force. And the difference is using which mu we're going to be using in order to analyze, to find that force. That is actually how we look at how we include friction into our analysis of static equilibrium. The last thing we need to talk about is that it's also very important that friction force, if we are analyzing a system, the frictional force that we're going to be using or we're going to be calculating may be less than the maximum frictional force. So it depends on the question. What we mean by that is don't assume that you're always measuring at this point, which means that your Fs equals mu s multiplied by n. This is not always the case. It depends on the question. So if the question says, well, we are impending movement, go ahead and use that. If the question is saying the object is moving, you need to use Fk, right? To find Fk by multiplying mu k with n. So at this point would be the lower value of it. So just because the object is not moving, do not assume the friction force is at its maximum of Fs. So if the question is saying to you that the object is not moving, we could be here or here. So don't assume the maximum unless it's been stated in the questions that that we have impending movement, right? That's the only time you will assume that we are going to be using Fs equals mu s multiplied by n. So I hope that clarifies a couple of concepts about friction. We talked about what friction is and how are we going to use it in equilibrium, which is the addition of another equation to the three equations of equilibrium that we have already learned how to use. And the fourth equation is the friction force equals mu, the coefficient of friction multiplied by n, and it depends on the question. If it is moving, we're going to use the kinetic coefficient of friction. If it's impending movement, we're going to use the static coefficient of friction. Thank you for watching, and in the following video we're going to state and list and explain the steps in order to construct the equations of equilibrium for a system that we will consider friction in, and we're going to solve a problem as an example of doing that. Thank you for watching. Until the next video.